Hey guys, welcome to another Kubernetes hands-on training. In this video, I'm going to talk about Kubernetes the hard way tutorial from Kelsey Hightower. Kelsey is a developer advocate at Google, and he in the Kubernetes community, he is known for his major contributions to the Kubernetes project, particularly at the earlier stages of the project. If you go to KubeCon, probably you'll get a chance to meet him and talk to him. This Kubernetes the Hard Way tutorial is super optimized for learning, and it gives you the perfect bird's eye view over the Kubernetes architecture. So it doesn't really go into depth of different components, but just how these different components are stitched together and make the Kubernetes cluster operate as a whole. I have forked this repository from Kelsey and added some additional documentation to explain some stuff a bit further. Added also some script to make things like spinning up VMs for the Kubernetes control plane and the worker nodes easier. Without further ado, let's dive right in. Alright, this is how the repository looks like. I have it open on my VS Code. Basically what you need to do is to go through this docs directory and follow the tutorial, just follow the numbers and perform the task. Let's start with the prerequisites, what we need to already have on our machine in order to create a Kubernetes cluster. And so we need a bunch of VMs, because as you know, Kubernetes is an orchestration technology. A server or Kubernetes control plane orchestrates the workloads running on the worker nodes. In our setup, we're gonna have a bastion host or a Jumpbox. This Jumpbox is actually the machine that we're gonna install a bunch of client tools on it and Kubectl. So you can think of it as a machine that we use to run Kubectl. And server is where the Kubernetes control plane runs, and most importantly, Kubernetes API server, etc. and so on. And the worker nodes are worker nodes, so they're basically where kubelet is running and listening to control plane and will spin up pods, deployments, and so on whenever control plane asks them to. So there's no restriction on this tutorial. Basically, it expects you to create 4 virtual machines running Debian 12 bookworm. There are probably so many ways of doing that. The way I did it on is that I'm using multipass. You can very simply run Ubuntu instances with multipass, and I've created a script called multipass.sh launch.sh. So when you see this one basically creates the VMs just like the mentioned in the prerequisites. So I'm gonna do it. I'm gonna run launch.sh to create the VMs. It's gonna take some time. So I'm gonna pause the video until Jumpbox server node 0 and node 1 are installed and running. Our launch script is now done. We have launched the Jumpbox, the server, and the 2 worker nodes. So if I now do multipass ls, I see that I have the machines and they're running, what kind of image they're running. If you're curious how we configured what image is used to run these machines, it is in here, this configuration, Debian bookworm, and this is the launch script, which is using this Debian Cloud init config that I just showed you. That's how the machines are created. So now what we just need to do to verify that we are running actually Debian and our ARM64 version of Debian, we can try opening up a shell, a multipass, or I have an alias for multipass like MP, shell Jumpbox, and I'm in Ubuntu. I'm in the Jumpbox shell. And if I run this now, if I try copying this over, we see that we are running an ARM64 operating system. So that's it for the prerequisites. Let's move on to the next step, which is setting up the Jumpbox. So now let's talk about setting up the Jumpbox. We have a shell here. We need to log in as a root. So one way to do it is that once we have the np shell of Jumpbox, we can just simply do sudo su and go to the root directory as this tutorial once. So let's just start by installing a bunch of stuff on our Jumpbox. Let's make sure we have git, curl, and stuff like that installed. Everything is installed, looking good. Now we're gonna clone this repository, not on our local machine, but in our Jumpbox, because remember, this is where we're gonna do all of our work. So let's just do that. I'm cloning not the Kelsey Hightower repository, but the thing that I created, because I have made some changes. So now let's just do this and cd into that directory. So Kubernetes the Hard Way. And if I do pwd, you see that we are in the root / Kubernetes the Hard Way. Very cool. Now here, this is our, let's say, reference directory. Now in here, we need to create a directory called downloads. So let's just do that. And we have a downloads.txt file in here. So basically, we're gonna run a wget command that reads from this downloads.txt, downloads everything, and saves them into this directory that we created. So let's just simply do that, nothing complicated. And let's just give it some time to download stuff. Very cool. Downloads are finished. So what are the stuff that we downloaded? If you look at the list, Kubectl, Kube API server, Kube controller manager, scheduler, like 10, 12 different items. And these are basically the Kubernetes components that some of them need to run on the worker nodes, and some of them only on the server or the control plane of Kubernetes. So we're gonna start by moving Kubectl, our Kubernetes command line, to our Jumpbox bin directory. So if I just simply run this, and if I do Kubectl version -- client, I'm gonna see that I'm running 3.28, exactly what we downloaded, and this is what the tutorial wants us to work with. So another thing that is that I always do when I install Kubectl in a fresh new environment is that I go here into bash rc and add an alias to my the end of my bash rc. Alias k is Kubectl. This is fine for now, but I usually add the auto completions and stuff, but for the sake of this tutorial, it's fine if we just leave it at that. So let's just source this, source, not source, source. And so let's move on to the next part. Part 3, provisioning compute resources. So here we are gonna move the stuff we downloaded on the Jumpbox to the Kubernetes machines, server and worker nodes. In order to move stuff over via SSH, this tutorial uses for loops and uses a file called machines.txt or machine database as a reference to store information about the different machines and stuff. So this file has 4 columns, and the IP address, what we get when we launch our machines, but which is specific to our own setup, and the FQDN or fully qualified domain name, the host name of the machines, and the pod subnet, which only makes sense for the worker nodes because we're not gonna launch pods on the Kubernetes server. So let's first start by looking at our machines. So these are my VMs. I have a Jumpbox and I have 2 worker nodes and 1 server. These are the IP addresses. And here in the root of my Jumpbox in the Kubernetes the Hard Way directory, I don't have any machines.txt, so let's just create a machines.txt and use this template to fill this file. And here I can simply replace, for example, the IP address of my server with what I have in here, which is 27, and for the node it's gonna be, for node 0 it's gonna be 28, and for node 1 it's gonna be 29. So I'm gonna save this file and exit out of it. The pod CIDR can be any valid CIDR, but this needs to be disjoint. So we want to have pods get a unique IP address on each node. So, and each node gets a disjoint subnet. And whenever a pod is assigned to a worker node, it will get an IP address within the range of its corresponding pod CIDR or worker node IP range. Now we have created the machines.txt. Let's configure SSH access. We want to, this script, as you see, uses a lot of SCP and SSH to run commands and move files over. So it makes sense to enable root login on our server and worker node. So let's just do that. So if I go to the server, for example, and sudo su and run this command to change the configuration of the SSH daemon to enable root login, and restart the SSH service, SSHD. Very cool. And I'm gonna do the same with other as well. So let's start another shell to node 01. So mp shell node 0 first one, and sudo su, and run this and restart the SSH service. Exit out of this. Do this for node 1. Same thing. Run this command. Let's switch to root. Run this command and run the SSH service. Restart. Very cool. So let's move on. And now here we need to generate some SSH keys on our jump host machine to be able to remotely run SSH commands on our server and our worker node. So let's just exit out of this worker node. Let's do SSH key gen here, and by default it wants to save the file, save the key as this path. Let's just use this other path, like I want the file to be IDRSA, not IDED something. So let's do it. No passphrase. Let's continue. All right, so now we want to copy the public key that we generated on the Jumpbox at SSH IDRSA pop over to our Kubernetes machines, the server and the worker nodes. We can run this, and right over here I've already done this. The key is already there, and so to confirm that the public key is there and we can run SSH commands or run commands and have a quick test to do to run this uname command. So you see, we get, when we run the uname on those machines for each machine, because they are all the same type, we get the ARM 64. Let's also set the host names for the machines. So when we want to SSH to them, we don't have to use their IP address. We can simply refer to machines with their host name, like root at server or root at node 0 and node 1. So let's use this command to set the host names of the machines. And once it's done, if you want to verify the host name setting, like print out the fully qualified domain name for each host name, you can copy this and paste this over and see what we get. So for each machine we get the FQDN, which is exactly what we want. So let's move on to DNS. For DNS, we want to first create a host file on our local machine and then copy this host file over to those machines. So let's just run these two commands to create a host file on our machine. For now, it's just empty. We are gonna run this command to copy stuff from the machines.txt to our host name. So when I run this and once again look at my hosts, I see now I have the correct IP addresses, the fully qualified domain names, and the host names in the hosts file. All right, now we want to use this host file. First of all, we need to use it on our jump host. So we're gonna append it to our jump host etc host file like this. We're gonna have a look at our etc host files on the jump host to see if our stuff are appended. And now we want to add the DNS entries to the remote machine. So basically do the same thing on the remote machines. Let's just run this command and we should be good to go. So far we have configured our Jumpbox and the Kubernetes machines with SSH communication and the DNS configuration so that we can easily copy stuff over to our machines via SSH and SCP command. Next step would be to have a look at the PKI infrastructure of our Kubernetes cluster, the certificate authority of our cluster, and the client and server certificate generation for different Kubernetes components. So the certificate authority configuration is stored at caconf. So if I simply do caconf, this is the configuration that we are going to use with OpenSSL to generate the certificates for our different components. So the first thing we're going to do is that we're going to generate a key for our CA, for our certificate authority of the cluster, and generate a certificate immediately out of our key. It's going to be like a self-signed certificate because we are using this -x 509 flag. So if I now look at, for example, the OpenSSL a request help to see what that flag means, I see this one will output a certificate instead of a certificate signing request. So there won't be any signing request. This is going to be like a self-signed certificate. In a production scenario, our CA or certificate authority of the cluster, the certificate for our CA or our root CA certificate needs to be approved and signed by the certificate authority of our organization. So let's just run the commands to generate the key for our CA root and immediately create a certificate out of it. So the result is that we have a CA conf and a CA certificate and a CA key. Now we have a certificate authority. We want to generate certificates for different components in our Kubernetes cluster. We're going to generate a certificate for an admin user of our Kubernetes cluster. We are going to generate certificates for the worker nodes, proxy, scheduler, controller manager, API server, and for service accounts that have the right to generate tokens. So script here uses the caconf configuration, what we have in our Kubernetes the Hard Way repository. Let's have a look at that. So I guess it would be even easier if I open it up here. So this configuration in different sections defines what is the purpose of, for example, each certificate. Is it used for CA? Is it a server and client certificate? For example, here for node 0, we're going to say the distinguished name configuration comes from node 0 distinguished name, which is here. These are the different attributes that will be passed to the OpenSSL to generate the certificate. You can have a look at this configuration and see how, let's say, properties and attributes are assigned to different certificates and how things are being shared or being inherited. We're going to look at our script. We're going to run it. Certificate, it's going to generate a private key. Then it's going to look at the corresponding configuration in the CA conf. It's gonna use that key and generate a certificate sign-in request, and then this certificate sign-in request is going to be signed by the certificate authority. The output will be a certificate, which is a certificate that can be used as a client certificate and a server certificate. Because, for example, if you look at the request extensions, the extended key usage for the component certificate is client and server. So let's just run this and generate all the certificates. Now we should have a bunch of, my certs variable was not initialized. So now let's just run it to generate all the certificates. Now we see that the client and server certificates are being generated. Now if you look at our directory, we see that for every component we have a CRT, we have a CSR and a key, and now we need to distribute it. So we generated the stuff. Now let's just distribute the certificate for the worker nodes. The most important component running in a worker node is the kubelet. So we simply run this. We just copy this to this directory on the remote machine or on the worker node to the kubelet directory. So let's just run this. Okay, now the kubelet certificates and keys are distributed. Also, we need the CA, the certificate authority certificate for whatever component. So they need to know their own certificate and the CA certificate. And now let's do the same for server. For the server, we want to distribute the API server certificate, the service account, and the certificate authority. For the server, I'm gonna copy it to the home directory. So let's just do that. And that's it. So I have also created another document here. If you want to know a bit better about this, learn a bit better about this PKI infrastructure at Kubernetes, you can have a look at that, see how keys are generated. Again, there's a cheat sheet, how things are distributed. And this diagram is also helpful to understand where the certificate authority sits and how different components use their certificates and key to communicate with other components in the Kubernetes architecture. It's worth mentioning that in our setup, etcd is using the same certificates as the API server, so we don't have a separate certificate for etcd or the Kubernetes database. We simply use the API server key and certificate for etcd. Let's move on. Next up, we want to generate the Kubernetes configuration files. So we generated the certificates and keys for different components in the previous section, and now we want to create kubeconfig files, so to say, for different components, for nodes, kubeproxy, and so on and so forth. These config files are used by the corresponding components to talk to the Kubernetes API server. So in each kubeconfig, you're going to have an attribute for the CA certificate, like the certificate authority, and the address of the API server, and the outcome of this command will be saved in a file called thatcomponent.kubeconfig for the hosts, or for the worker nodes. The outcome we're going to be like node 0 kubeconfig. For kubeproxy, it's going to be kubeproxy kubeconfig, and so on. So let's just generate these files, generate these kubeconfig files by, let's start with the worker nodes. Let's just run this script. So now if I look at the directory, we have right here node 0 kubeconfig, node 1 kubeconfig. So these config files, as I said, is going to be used by kubelet to talk to the kube API server. So let's generate the kubeconfigs for kubeproxy, and let's run the next part, generate the kubeconfig for controller manager, and the result is theirs. And let's run this script to generate the kubeconfig for kubescheduler. And the last one, I guess, is this one. generate the kubeconfig for the cluster admin. And now we generated them. So if I now grep for kubeconfig, I see we have admin, kubecontroller, manager, proxy, scheduler, node 0 and 1. Now let's just distribute these config files first for the worker nodes and also for the server. Simply copy the kubeconfigs to the root to the home directory of the server. Awesome. So let's move on to the next part. All right. So next up, we need to generate an encryption key, which is used by etcd to encrypt data at rest, not at transit. So when we store, for example, when we create secret resources on our Kubernetes cluster, they are going to be encrypted using this key and stored in the etcd database. So let's just generate 32 bytes and pass it to base 64, encode it in base 64 like this. Now we have our encryption key, a random thing that we generated in this variable. And we have a configuration here called encryption config that we're gonna basically replace this placeholder with what we assign to this variable here and create this resource so that a API server or etcd will pick this up and use this key for encrypting secrets. Let's replace it. Okay, now we have our encryption config, and we don't apply it yet because we don't have any API server up and running. We simply copy it over to our server like that, and let's move on. All right, so next up we want to bootstrap our etcd cluster. Etcd is a distributed key value data store that acts as a Kubernetes database. When we apply configurations, everything will be persisted in etcd. We already downloaded it in our jump host. So next we want to copy this stuff over to our server, and here we need to run the following commands in the server. So let's just SSH to the server from our Jumpbox. Now we're in the server, and let's look at here in the root directory, in the home directory of the root user, we have the certificate and the stuff that we downloaded. So everything that we need for etcd is there. Let's just extract the etcd binary and move it to user local bin. I use the API server key and certificate that we generated also for etcd. So now this is done. And we also have an etcd systemd unit file. So let's just move the etcd units to the systemd directory and reload the system controller and enable etcd and start it. All right, so if I now do systemctl status of etcd, I see that etcd is running. And if I run this command to verify the status of my etcd cluster, I see now I have like 2 replicas of etcd distributed database running on the same server on the same machine on different ports. So everything is fine. Let's move on to the next step. All right, so next up we're going to bootstrap our control plane. We downloaded a bunch of stuff on our Jumpbox. Let's just move them over to our server by running this command. All the system, the units, the binaries, and the configs. Let's move the files over. And the rest of the commands need to be executed on the server. So let's SSH on the server. Now we're on the server, the root directory. We have all the configs, all the stuff that we need. First off, we need to create a directory for storing the Kubernetes config. Let's move the binaries to user local bin and give them execution rights. And Also, let's create this directory varlib Kubernetes on the server and move the certificates of our control plane, API server, service account, encryption config, and kube API server stuff into the varlib Kubernetes directory, and also move the unit file for our API server, systemd unit file, to the systemd directory, and give it a name, kube API server service. Next up, we need to move the kubeconfigs that we generated into varlib Kubernetes. Let's move that, the kubeconfig for controller manager and the systemd unit file of a controller manager to the systemd directory. Same thing for the scheduler. Let's do that, and some configuration for kube scheduler that we're gonna move to the directory we created for Kubernetes configurations. Next up is moving the scheduler systemd unit to the right directory. And now we have the units. Let's just start our different components. It will take up to 10 seconds for the Kube API server to be up and running. So I guess now 10 seconds is already passed. Let's just do status of Kube API server. And now we see that it is running, which is good. So if we want to verify it, we can use the client or Kubectl client and use as an admin, try to talk to the Kube API server. Let's just run this command, see if from the same server, our Kube API server is running on port 6443 of the same machine, localhost, which confirms that Kube API server or the control plane is up and running. Next thing, we need to assign Kube API server a role that basically gives it the permission to retrieve metrics and logs from the kubelet API. So if you look at the configuration, if you look at the Kube API server to kubelet configuration that we're going to apply, we basically create a cluster role with this name, with this permissions to basically read all this stuff, be able to read all this stuff, and then we bind this role to our Kubernetes user. So let's do it. Let's apply this. The configurations, everything is there, and let's verify that we can call the Kubernetes API server. Let's just exit out of the server and try to hit the Kubernetes API endpoint to just get the Kubernetes version from the Jumpbox. So let's clear this and run this, and we see that we are running Kubernetes 1.28 in our control plane, and we could successfully retrieve the version of Kubernetes from the Jumpbox. So let's move on. So now let's talk about bootstrapping the worker nodes. As we know, the most important Kubernetes component running in the worker nodes is kubelet, but kubelet itself is sort of an Kubernetes agent or an orchestrator that can only perform its task by calling other components and is dependent of other components, namely the container runtime and the other interfaces that sit in between kubelet and the container runtime. We have a bunch of scripts in here. We can simply run them, but it would make sense to have at least a brief overview of what other components are involved with this configuration. So let's have a look at this documentation that I have created. This one, CNI container guide. So let's open it in preview. In order for kubelet to do its task, we need at least 3 components: a container runtime, a container runtime interface, and a container network interface. Container runtime is in charge of managing the lifecycle of a container. In our example, we are using containerd. It can be other options like Cryo or Docker. Container runtime interface is sort of an interface that sits in between kubelet and the container runtime, and kubelet instructs the container runtime to perform certain actions. CNI is the networking interface that is a specification and a set of plugins that implement the container networking. So namely, when a pod is created on the or assigned to a node, it should get an IP address. It should be able to talk to other pods. There is a pod running in another node in our Kubernetes cluster. Our container assigned to that pod, running in that pod assigned to our node, should be able to communicate with other containers in other pods assigned to other nodes. So that's the Kubernetes networking model. So if I scroll down, I have this diagram in here that basically shows you the flow. If a pod is assigned to a node, Kubelet will call the CRI plugin to create a pod. So it will indirectly instruct containerd, hey, I need a container. And the CRI plugin will create a network namespace for that pod, and will then call the CNI plugin to take care of the networking aspect. Like CNI plugin called bridge is executed to connect pod to a virtual bridge interface, and also the host local plugin is executed so that the containers inside the pod can refer to one another with localhost. Once we get the IP address back, the kubelet will call the CRI plugin to do the container lifecycle operation to fetch the image and start the container. So if you want to go into the depth of how containerd is configured, I've put some explanations in here. Please go ahead and check it out. But for the sake of this video, I'm gonna skip this part and go back to the documentation. For each node, we have a pod CIDR or disjoint subnet. So pods assigned to, for example, node 0 can only get IP addresses in this range, and pod assigned to node 1 can also get IP addresses in this range. What we're gonna do is that we're gonna change the configuration that is used by CNI to create that bridge interface and get the IP address and so on, to use this subnet. This subnet is sort of a placeholder in this configuration here, and we're gonna replace it with our pod CIDR. So let's just do that. Let's run this script on our Jumpbox, and also let's move over the binaries and the systemd units over to our worker nodes. And so the rest of the operation need to happen on the worker nodes. So I just SSH here to node 0 and run these commands. So install a bunch of software that is needed for example, Kubectl port forward, the socketcat library. So also it is recommended that we disable memory swap on our worker nodes. Let's create these directories to store the binaries of kubelet and kubeproxy and so on. And let's also run this script to create to extract the binaries out of the archives and move the binaries in the right place. Also, let's move the config files in the right place for the CNI container networking interface. Let's configure containerd by running this script and moving the configurations in the right place. Same thing for the kubelet binary itself and moving the systemd unit to the right directory, and the Kubernetes proxy as well. And let's just start the daemons. So we are gonna exit out of node 0, do the exact same thing on node 1. I'm gonna pause the video and perform this exact same operation. If we now go back to Jumpbox and here try to run this command on our server, you see that both of our worker nodes are ready because all of the components on the worker nodes are now running and active. The daemons are running and everything looks fine. So we get the same output as expected. Let's move on. Next up, we want to configure Kubectl for remote access. So instead of calling Kubectl via SSH on the remote, on the server, we want to be able to call Kubectl on our Jumpbox. So we're going to create a kubeconfig file which is going to use the exact same configuration as the one we created for our admin user. So if I fall on the Jumpbox, I can reach the Kubernetes API server by running this command. I can get the version, but to be able to authorize myself also as an admin, I should create a kubeconfig. So let's just run this command to create a kubeconfig that will be stored in the default directory of Kubectl. Now I have the kubeconfig, and if I now, for example, look at the kubeconfig, this is my kubeconfig. I can run ik version. I can get the version, and also I can talk to the Kubernetes API server. Let's move on to the next part. So when we bootstrapped our worker nodes, we configured CNI and kubelet and containerd in a way that whenever a pod is created, it will get an IP address and automatically a bridge interface is created. And the pods assigned to a certain node can talk to other pods assigned to the exact same node, but they cannot talk to pods being assigned or scheduled on other worker nodes. How can we implement the Kubernetes networking model? The Kubernetes networking model basically demands us to enable communication between pods no matter on what node they are being scheduled. So one way of doing it is to just simply add routes. We have here in our setup, we have only 3 machines, 1 server, 2 workers. We can simply get these variables from our machines txt and add the routes, the corresponding routes. So we tell the server if you want to reach out to any pod in this subnet, in the CIDR subnet of node 0, you can, the route will go through the IP address of node 0, and same thing for node 1. And for the worker nodes, they only need to know about the other node. Let's just run this. Let's also run this. And this one. To verify the thing, let's just check the routes of the server. You see now we have our routes added in here, CIDR routes. You can also check the routes of the node 0. See if it's also taking effect. You see the route for node 1 is configured on node 0, and also the route for node 0 is configured on node 1. So let's move on. We configured our Kubernetes machines and different components. We brought the processes to a running state. We also configured the networking aspects and the routes and so on. So it's time to perform some operations and do some smoke testing on our cluster to see if it's actually working like a Kubernetes cluster. We're gonna start by testing the etcd encryption at rest. So let's create a secret called Kubernetes the Hard Way with some literal in it. So if I now get the secrets, I have my secret in here. Let's get a hex dump of our secret from the etcd database and look at the hex dump. So we're gonna run this command remotely on the server and get the hex dump of the etcd for our secret. And we see that the key 1 is used to encrypt the data and the algorithm, just like what we configured in the encryption config. So this test passed. Let's test creating a deployment. Let's create a deployment simply by running this command, a simple nginx deployment. Let's see if it works. And if we get the pods, we see that the Nginx container is being created. So if I just wait a bit and keep watching this, you see now the Nginx container is running. Awesome. So this one also passed. And also test the port forwarding. So let's just, if we want to forward the port, we should get the name of the pod and then perform this. Nginx is running on port 80. We're going to map that port to 8080 on our Jumpbox machine. So if I now open another terminal and get a shell on the Jumpbox and run this command, I can successfully hit the Kubectl port forward endpoint of Nginx. Cool. So let's move on. I don't need this anymore. And let's test the logs of my pod. So let's just do this. I can see the logs. This one also works. And I can also perform exec. So if I just run nginx-v command in my nginx container, I see that the version of the nginx is successfully returned. Let's test the services. If I want to expose the Nginx service as a node port service, let's just run this command. Service is now exposed. If I want to get the node port of the node port service I just created, it is stored in this variable, and I should be able to, as the nodes is in the same network as my Jumpbox, I should be able to basically hit that endpoint by running this command. So this should basically work. This doesn't seem to work. Maybe the pod is simply honest. Let's get the pods and let's describe the pod of Nginx here. Let's see on which node it is being assigned. It is being assigned to node 1, so this is wrong. So if now it is exposed as a node port, but I should use node 1, and now this works. So you need to make sure if your Nginx pod is being assigned to the right node. So our test pass. Seems like our Kubernetes cluster is not really looking like a production cluster, but it is behaving like a Kubernetes cluster, and we managed to finish this tutorial. That's awesome. So in the last step, we need to clean up. I have created a script for that. If I go to my Kubernetes the Hard Way, the cleanup script will just take care of everything. It will just use multipass to clear things up. So just to clean up, we stop everything, we delete all the images, and we purge, so nothing will be left over. Okay, and now that's it. So if I now run mpls, I have no instances. Alright, my Kubernetes cluster is gone. Alright, that brings us to the end of the tutorial. As always, I hope you liked the video. If you did, please give it a like and show your support by subscribing to the channel and sharing the video with your friends who are into learning a bit about how different Kubernetes components are stitched together and work together. Thank you for watching, and see you next time.